Hello, everybody. Welcome to the 11th seminar of the EVEREST project. So this is kind of the first one in the second round. And today we'll be talking about what we call a system development kit. I'm just gonna tell you what that is in a minute. So first of all, my name is Jeronimo Castrillon, and I will be presenting this seminar with colleagues from TU Dresden, Karl and Felix, also with colleagues from IBM Zürich, Burkhard, and colleagues from the Politecnico di Milano, Stephanie and Serena. So it's going to be a heterogeneous webinar with a lot of contributions from different people. Okay, so let's get started. As you know, we have been posting different videos about the EVEREST project in this channel. Just as a reminder, the EVEREST project is a European project where we tasked ourselves with designing an environment to simplify the programmability of high-performance big data analytics. And the focus here was strongly on heterogeneous systems, especially those with reconfigurable hardware, things that are distributed and scalable, and that should be also secure. Okay, so this is also something that we mentioned already in the past. So basically, all the development within EVEREST project is driven or steered by several use cases, and these are actually quite complex use cases, large use cases, for instance, in the area of renewable energy prediction or air quality monitoring and traffic modeling. So these are interesting use cases because they combine aspects of big data, aspects of high performance computing, and of course also aspects from machine learning. So the webinar that we're presenting today is very related to the fourth EVEREST webinar, where we talk about domain-specific languages for heterogeneous and emerging computing systems. So the idea there was to reason about what kind of new programming models, what kind of languages, how can we talk about domain-specific languages for some of the components within these large use cases, so that we can actually do better and optimize a lot just by using novel tools. So these are the use cases that we saw before. And in that webinar, we touched upon things on how to handle irregular coarse-grained data flow. And so we talked about a language there. We looked at HPC kernels and how can we use domain-specific languages to represent those kernels. And in the third use cases, we used to motivate ML-based decision-making and how then to integrate as well inference of large models. And one aspect that we discussed also in that webinar is that our aim with these languages, with these tools, was to have kind of a converged infrastructure. And back then, a year ago, more or less, we discussed that we were aiming at trying to achieve this convergence using the MLIR compiler framework. And today, you're going to see a lot of that through the demonstration where MLIR is used and how we use MLIR to actually achieve convergence of abstractions and how can we reuse those abstractions also across different domains. Another webinar that is actually quite related to the webinar that we're discussing today is the second EVEREST webinar, where colleagues from Politecnico di Milano actually discussed the Bamboo HLS tool. So here I have some images from that webinar. And basically that webinar was focused on advanced high-level synthesis features of the tool, including how they handle function pointers, integration of handwritten modules, advanced features of C++11, and also MLIR interfacing, which is also very interesting from the point of view of what we do with compilers. And last but not least, they also discuss OpenMP support. So what is this webinar about? So as I said at the beginning, we're going to talk about this system development kit. So what this is actually kind of bringing a lot of different things together, in part what the languages, the compilers that we discussed before in previous seminars, but also high-level synthesis tools. The idea is to bring these languages, tools, and methods so that we can actually simplify the deployment and also optimize the execution of large use cases in heterogeneous systems. So this webinar is going to be structured as follows. So here you see again the three use cases. So we're going to touch upon the aspects of languages in sections 2, 3, and 4, the general tensor kernels, and the data flow pipelines in section 3 and 4 were also discussed in the webinar number 4. Today we're going to explain a little bit better how the DOSA framework works for machine learning kind of workloads. Then we're going to discuss how from these different input kind of use cases, input models, we achieve integration so that we can actually handle these different components jointly within the EVEREST flow. And then, of course, we go into synthesis of kernels through Bamboo, and we will discuss today a new tool that we call Olympus. And this tool is what actually allows us to put the system together automatically with hints from different tools upstream in the programming flow. You may be wondering where the one is. So the one is what we call the Basecamp. So the Basecamp is the current version of a tool that we use to actually steer everything that is happening below that Basecamp, right? So it's kind of a tool that allows for some convenience commands so that actually you can use the different flows without maybe having to deal too much with the details of the flows. So with that said, I would like to give the word then to Burkhard, who is going to explain how this Basecamp is constructed in general, and already give some examples of how to use it. Thank you very much. I hope you enjoyed.
Thank you also for the kind introduction and the kickoff of this webinar. Yeah, good morning, good afternoon, good evening to all of you. Thank you for your interest in this webinar. I'm Burkhard, and I will guide you through the next two steps of this webinar, namely the Basecamp tool and the introduction of the EVEREST Machine Learning Inference Pipeline, or the DOSA tool. Let's start with Basecamp. Basecamp is the facade compiler of the EVEREST SDK, so it's a single entry to all different flows. To simplify the usage for the user, it wraps all components together. As I said, it's a single entry, which is also logically because we have only a single exit. That the EVEREST runtime, where that's the point where the EVEREST compiler toolchain hand over to the next step in the process. The EVEREST Basecamp tool wraps all components together, but it also has a modular design so that users only depend and need only to install the tools that they really need. And since we are in the EVEREST world, a Basecamp is always a good start for all EVEREST endeavors, so to speak. Basecamp has a command line interface, which is displayed here, and you see all the different flows that are supported: data flow, HPC, machine learning inference. But that's only a wrapper, because actually Basecamp is an interactive Python module and provides the respective API as displayed here. You could use it, for example, in a Python notebook to interact with the tool and to set steps iteratively and to interact on a fine modular basis, which we thought is a much more usable approach than just a command line interface. And actually the command line interface is, as I said, just a wrapper around these Python API. So one of the flows the Basecamp tool supports is the machine learning inference flow, and now we go into detail for this one. The machine learning inference flow is also called DOSA, so that's the name of the tool that we also use in other types of publications. And DOSA has two names. One is the distributed operator set architecture, because we target distributed FPGAs, and we use the operator set architecture concept to solve the problems of compilation on the way. And DOSA is also a very delicious Indian dish. Yeah, DOSA was intended to be, so to speak, one tool to rule them all, to cover a large solution space, cover different optimization, and supports major standards. So that's why we start with Onyx as input. But one other theme that is important to us is that it avoids reinventing the wheel, because as you, as informed participant of this webinar, know, is that there are hundreds of papers out there that discuss how to optimally implement one part of a deep neural inference on one FPGA, one specific convolutional neural network on an FPGA, one part of a convolution, specific convolutions on specific FPGAs, and so on. Throughout this project, I read roughly 200 papers around how to do deep neural network inference on FPGAs, or how to optimize specific parts. And for this full body of work, some of these tools are even open source. For example, TVM, HLS for ML, Hadoop, VTA, VHDL for CNN, and so on. Fin, another name. So our idea was to avoid reinventing the wheel and not just writing the 201st paper with just doing the same what others did, just with a different name and for a different project. But our idea was to avoid doing this, to avoid reinventing the wheel, and to reuse these richness of the open source research community instead, and to combine these tools and combine them in an optimal way. That's why DOSA does not only have the ONIX as input and the target constraints, such as how much performance we need, but also the available third-party frameworks as input, and we need to analyze them. And then with this analyzation or characterization, which requires a unified performance criterion, DOSA can find the best combination of all of them. For this analysis, we have use a Ringlein analysis. And with this Ringlein analysis and the input of the characterized third-party frameworks, we can decide how many FPGA we need, which layer of the input deep neural network ends up on which FPGA and which architecture we use. That's completely automated. And then in the end, a third step, we also generate the communication logic and the glue logic to put everything together, and something like build scripts and so on. And as said before, we target explicitly distributed FPGAs because on the one hand, models become larger and larger. That's quite present in current days. And on the other hand, there exists, it also has economic reasons, because usually if you have two medium-sized or small FPGAs, they are cheaper, but still more performant than one large FPGA if combined in the right way. That's why DOSA explicitly aims for distributing deep neural networks. As I said, we use a Ringlein-like analysis to decide which part of the network end up on which FPGA and which architecture we use. And I'm sure you are familiar with Ringlein analysis, so here's depicted one. But in contrast to classical Ringlein analysis for FPGAs, we have multiple roofs, here depicted in green, red, and blue, because we have multiple bandwidths, either different types, also orange here, different types of memory within the FPGA, or even the network bandwidth for network attached FPGAs, because they end up directly in the FPGA logic and are therefore some kind of memory. Or they have the same bandwidth constraints from a Ringlein point of view. As you can see, the variety of the kernels vary a lot, so it's a huge variety. And that's because we have, for every kernel, we have different options available to implement them. These options can be grouped in two types. One is the so-called engine type accelerator, which is depicted here on the left-hand side. And the engine type accelerator is a typical overlay accelerator that has a control unit and features an arithmetic logic unit, usually a matrix vector unit, like a GPU or a tensor processing unit, so TPU. But in contrast to them, we can adapt the specific operations of this matrix vector unit and the size to the problem at hand. On the right-hand side, we have the other type of architecture, the so-called streaming type accelerator, where the complete network is rolled out and flattens throughout the FPGA. So every computation, for example, a convolutional kernel within a convolutional layer, has its own dedicated circuit. So the weights are baked into the FPGA logic. We don't need any memory access. As you can imagine, this requires a huge resources, but could also provide tremendous throughput. So we need to find the best trade-off between these architectures. And to do so, DOSA starts, as I said, with the ONIX as input, and we build the abstract syntax tree, or AST. And then we analyze this AST on quite a high level. As you see in this example, that's a printout out of the relay IR, so the intermediate representation of the TVM framework, or domain-specific language for deep neural network problems. And we analyze this at this level. So as you notice, that's not multiplication or for loops and so on. That's quite high level, and that's necessary because it's somehow meaningful for us. And we annotate the AST at this level and annotate for a given performance goal. So for example, 5,000 inferences per second, how much performance each operation needs, what the different operational intensity for the different architectures are, and which framework can possibly implement that. This concept is called operations set architecture, and that enables finding the best trade-off. And one example here is depicted in this figure on the left-hand side, the bandwidth of a typical convolutional neural network. So in orange, the output bandwidth, in blue, the input bandwidth in gigabytes per second. And as you can see throughout the network, so throughout the layers, it decreases. While the parameters are also depicted here in yellow, and they increase throughout the network, which is somehow typical because in a usual convolutional network, you have convolutions at the beginning and more compute-intensive workload operation at the end, like dense layers or fully connected layers and so on, or general recurrent units. And that's, with this analysis, we need to find the best trade-off between slow, but as relatively slow, but resource-efficient engine-type accelerators, so maybe for the end of the network, and very resource-hungry stream-type accelerators that also could provide a huge throughput, which would maybe fit for the beginning of the framework, of the network. And DOSA automatically finds the best trade-off. But one thing that DOSA needs to do so is another as a unified evaluation criterion for these operations. As I said earlier, we have annotated the abstract syntax tree originally with floating point operations per second as local performance constraint, but that flops on FPGAs are quite meaningless, so to speak, right? Everything could be a flop. We can 2 gates to add 2 1-bit numbers would be theoretically a flop, floating point operation, or 500 gates to do 32-bit multiplication is also a flop. So it is highly meaningless, highly flexible on FPGA. So that's why we decided to do iterations per second for a specific unit under consideration as performance constraint. This sounds on the first hand maybe generic, but since this iterations per second is always tied to a operations that we currently analyze or a combination of operations. So for example, the max pooling convolution we would put into this FPGA, we can combine them and then analyze the combined iterations per second, or we analyze the complete iterations per second for one FPGA. And that's quite meaningful because it's tied to a domain-specific language. And that's how we were able to automate or to find this best trade-off using the operations at architecture. Most importantly, this iterations per second unit is also compatible with a roofline analysis as depicted here. It looks the same like other roofline analysis. And here you have the roofs, it's just a little bit moved to the left. And the meaning is the same. So the more you go to the left, the more you are constrained by bandwidth, and the lower is the operational intensity. And you can also calculate the complete iterations per second for one FPGA, done here with a violet line. Another core concept for operators for DOSA are the operators at generators, because we need to automate the way we reuse third-party frameworks. We don't want to spend a lot of coding there. And that's why we invented this concept of adapters or operators at generators or OSGs that are asked, so consulted throughout the compilation framework. So we start with the ONNX, and then here we have the abstract syntax tree and do the analysis as depicted in the slides earlier. But now we want to know if a specific convolution or a specific pooling can be implemented by a framework. So we just ask the framework and say, please provide me how much, if you can implement this operation, and how much performance we would get in iterations per second, and how much resources it would cost. And then each of these operators and generators can answer with 0, 1, or multiple options that are then quite efficiently annotated in the abstract syntax tree, used for the design space exploration. And after the DSE is done, we can ask, then say, okay, we decided for one specific implementation, and then say, now please implement what you have offered, stick to your contract, so to speak. That maybe that's a quite important concept to automate the reuse of third-party frameworks and hence to avoid reinventing the wheel. Besides this, we also need communication between the within the FPGAs, but also between the FPGAs, and between the FPGAs. We can stand on top of our previous research, the serial MPI framework. It's just open source, and you can check it out here. As a teaser, the serial MPI framework is a hardware agnostic communication framework, and it could also synchronize CPU and FPGAs, so hardware agnostic. It provides the respective libraries for FPGAs and CPUs. And for the FPGA side, the message passing logic sits within the FPGA, and also the network stack sits within the FPGA. That results in a very, very low round-trip time and latency for these MPI framework on FPGAs. And I printed here one number, round-trip time below 30 microseconds for the complete stack. So application to application on different nodes. And that's a framework DOSA can leverage to distribute applications. To briefly analyze the efficiency of operator set architectures, we put together a model zoo with some models and then analyzed how much resources they would use and what the performance we get and what the combined metric is, the efficiency. And as you can see, they vary largely, and the efficiency varies of 2 orders of magnitude. For example, here in the lower plot, you see that for specific networks like the MPCNN, it's the same network, and different combination of third-party frameworks have different orders of efficiency, so how much performance per resource we get. Also here for LINET and VGT and so on. But also specific patterns emerge, which combination of frameworks are best for which part of network, and that's what we may want to research in the future. Besides that, we also want to compare DOSA to the state-of-the-art tools. And here our main aim was to simplify that, because as I said earlier, the issue is not that there are no tools that could implement some DNN or CNN on some FPGAs, but they're limited or difficult usability. So users need to know what FPGAs they want to use or what FPGA architectures they want to use. They maybe need to code something within an FPGA specific language. And DOSA avoids all of that. DOSA supports a major community standard, foremost Onyx. It does not require the user to have any knowledge about FPGAs. It is one click to compile the Onyx to FPGAs. Then we can offload the build to a build server. That's another click, so to speak, because building FPGA files, as you know, requires some time. Then DOSA also generates the deployment scripts. So that's another automated step. And then also the execution is automated. And one major feature is that DOSA supports up to 100 FPGAs in parallel, or if you have clusters, it's even more, in contrast to major state-of-the-art tools. Also, the design space exploration is very fast and takes always only a few seconds. To show you some concrete results for this medium-sized CNN that is rolled out completely, so we aim for really high throughput. We need 9 FPGAs, and then the results are printed here in this plot and written here on the left-hand side. And for CPUs, we have 50x speed up and 80x more efficiency. And for GPUs, 9 FPGAs are nearly 20 times faster and 30 times more efficient than one GPU. And the end-to-end latency is below 0.3 milliseconds. So really low latency processing for this inference, which is also depicted here on the second left plot. And this huge gap between one CPU or one GPU and 9 FPGAs in the latency results from the efficiency of the cloud FPGA platform, which we introduced in an earlier webinar, the first webinar of the EVEREST project. And it's mainly due to their network attachment and the processing of the communication within the FPGA and the disaggregation. And of course, the massive parallelism we use. So we roll out this medium-sized network across 9 FPGAs. And that's why we achieve this very, very high throughput. And yeah, but for more details, you can check out the first webinar about the cloud FPGA platform. If you want to know more, you can also visit GitHub, because DOSA is open source, so you can check it out and use it. We have also put all publications together, so if you want to have more talks, more background, more concept, you can visit this link. And even more literature you can find on the Cloud FPGA project page. And without further ado, we now switch to a live demo of all of these concepts. And so here we are. I also added some subtitles for your convenience. So that's a network we want to show. And that's similar to the network I just showed you on the slides. But we aim for, it's a little bit smaller, and we aim also for smaller throughput. So that's why we need then less FPGAs in the end. Here are the constraints file that I mentioned. We have the name, we have the input dimension, which is technically necessary for the ONNX file. We specify how much performance we want, and we specify which resources are available, which type of FPGA I mean by that. Now we invoke DOSA, and this I used the command line interface of DOSA or the EVEREST Basecamp tool for convenience, but this could also be done using the mentioned Python API within a Jupyter notebook, as showed earlier. But it's easier to demonstrate for a webinar using the command line, because you see more on one page. So now we start DOSA, and this is not accelerated, so that's fully real time. And as you can see, the complete design space exploration is already done. DOSA also installs all the necessary dependencies for building and deployment. And then, as you can see, also some figures will be generated, some insights, which we'll discuss later. And all this complete build for 6 FPGAs took only 15 seconds. And here you see that's the build files, and that's all the 6 FPGAs we need for this network and to achieve this 2000 samples per second. DOSA explains also the best, what the reasons are, what performance is achieved in the end, what the architecture is in details in a very long JSON file, if the interested user wants to know it. Also what the utilization is and so on. The input dimensions of every single step, so all the reasoning the compiler did. And here I created a plot for how the architecture looks like, so that how many FPGAs implement which layer. So here we need 6 FPGAs, and here now we can discuss the roofline plots with flops and with iterations. So DOSA provides the input to the information to the user with both metrics, depending on how he is more convenient with. And it does also the bandwidth analysis as showed you before, and the throughput analysis to provide insights to the user so that the user can understand what the reasoning of the compiler was. So now that is somehow combined these figures, how the bandwidth is distributed across the layers and the throughput. And you see where the bottleneck in the throughput is. And to demonstrate that, we now want to generate a new network that has not only 2000 samples per second, but 6000 samples per second. And for this, we open the constraints file again and change the target throughput to 6000. So triple it. And now we invoke DOSA again and wait again 10 seconds. And we just, for demonstration, we disable the generation of build scripts because we don't want to overwrite our previous scripts. And here you see that we now need some data parallelism to overcome the bottleneck in the last layer, or in the last layers actually, which logically have an engine mode, or in this time even not an engine mode, but are the slowest type of accelerator in the network. And that's why we need to double these FPGA to make this throughput work. Now we remove certain operators and generators that are available, which is possible dynamically at runtime. And now to demonstrate the flexibility of DOSA, but now DOSA cannot find any solution, but informs the user about this too, that for certain operations, there's no library available that could implement it in the FPGA. So back to the original and successful build. Here's a build script that is generated that could be offloaded to a build server and then build all the FPGA files. And now this takes several hours, which we did cut out for this video. And here you see then that there are the bit files for every FPGA in specific folders. And we use partial configuration for scale out of the deployment for the FPGAs. So besides the build script, Dosa generates also a deployment script, and now we demonstrate this usage. And we deploy the cluster on the IBM Cloud FPGA platform. Here's the second time we did a cut in this video, because this would also take a couple of minutes to power on all these FPGAs and to distribute the bit streams. And finally, we do a demonstration of this network compared to a local CPU demonstration, compared to a remote inference as a service server, but with a CPU, and compared to this remote network attached 9 FPGAs. Also, the script is generated by Dosa, and now we execute it. And now there will be hashtags to demonstrate you the progress of the inference. And although this is not accelerated, so here you see the speed of 1,000 inference requests for the CPU, and now the same inference request to the a remote CPU sitting next to the FPGAs we will use in a second. So to demonstrate how fast FPGAs are. And now you will see that so quick 1,000 inference is done with using 6 FPGAs generated by Dosa. So, and that's the speed up Dosa can generate. And with that, I hand over to Karl to demonstrate what the EVEREST SDK can do for HPC workloads.
Thanks, Burkhard. Now we're going to be looking at the general tensor kernels. Now, we've already looked at those in quite a bit of detail during the last webinar. But in this webinar, we place more of the focus on how the SDK integrates all of those things. So we'll be iterating on some of the concepts we saw last time and see how they integrate in the bigger picture using MLIR. Now, last time we already hinted at how MLIR was be used to apply domain-specific transformations and to make these HPC kernels be first-class citizens in the flow that we are making. However, we haven't looked at how third-party components can be used in this type of flow. Specifically, we haven't really looked into how the MLIR infrastructure makes that possible, and also how we divide the responsibilities in this flow into application and domain-specific parts, platform-specific parts, vendor-specific parts, and third-party parts. Now, this figure is supposed to give you a short overview of some of the things you've already seen and things that you will be seeing. At the top left, we can see the abstractions we were using in the last webinar to handle HPC applications. In the last webinar, we were using CFD-lang, which for the EVEREST project, we have now upgraded and changed to EKL, which is the EVEREST kernel language. It is the same thing in most regards though, so it won't be presented again here. We've also seen Tile, which is used to optimize this. Now, this tackles the kernel from an algorithmic standpoint. But in order to integrate it into the EVEREST platform, we also need platform-specific parts, description parts. This is EVP and Olympus, which are also MLIR dialects you will get to know during this presentation. There's also the DFG dialect, which serves to represent the data flow applications, which we'll see in the next segment, the data flow applications, I mean, but also to provide the overall integration of these flows between host and device. There's something on the right which you haven't seen yet, which are number representation specific things. Those are on the vendor end in our kind of view and serve to make the reconfigurable platforms accessible towards the MLIR user. These are also provided by us in this case. And obviously there's a wealth of core dialects that make this all easily connectable and more usable and reduce the amount of code the webinar has to bring, the SDK has to bring into this flow. Now, Following the example from last time, you might remember that we started with some sort of kernel program. We will skip the translation step from the DSL and we will replace CFD-lang here with EKL, but that's basically what we began at. Now, this was the level to which we took the last webinar. Although we did code generation, we didn't highlight how different levels interact here. You can see that more clearly if I start to lower this or concretize this to a particular implementation. Now here we translated the previous program to the tile dialect, which performs the tensor-specific optimizations, but we also introduced a parallel abstraction here that can exist at the same time as tile, but on a completely different level, which is base 2. That is concretizing the scalar we are using, and that's something specific to how we want this to be handled in recurrent figurable compute. Now, going one step further, we have to concretize the schedule of what we were just doing. The tile operations helped us to do this from a mathematical standpoint, improve our algorithm from a complexity perspective, but then we have to go to a particular loop schedule, and we can do this via the call-in dialect. So this is the translation of the program you saw earlier, and in fact here we still have base 2 around, and now we would go about adding more platform-specific parts to this. But this is only a single kernel. The kernel itself needs to be integrated in the entire host program. Some of that will be done using the data flow abstraction. The rest has to be done on a different level. That level, we've already mentioned last time, is unfortunately something that is extremely hard to automate and does require user intervention. And that is modifying the existing application. Last time we talked about how this would be done on a kernel level, how you'd rewrite to DSL, how you go for idiomatic and clarity of intent code, and actually could save quite a few lines there. But on a more fundamental level, this also means modifying the build system of the project you're using. And those are very different from application to application. So there's no good one-size-fits-all solution. However, in general, we suggest doing the following, which is moving to a statically linked stub with a dynamically linked plugin. The dynamically linked plugin will be created by the SDK. The statically linked stub is derived from the interface of the kernel and is what your existing application has to be modified to call into. Now, these stubs could technically be automatically generated in the presence of pragmas and parsers for your existing input language. But with projects like Fortran, this might be very complicated considering all the different standards that may be in use. However, the amount of work needed to do this stub is quite simple, or should be quite low. The modification of the build system is unfortunately not avoidable, and that could take a bit longer. The architecture of this plugin is then we provide this dynamically linked library that the system will be using, and that collates all of the different SDK parts. That includes the bit streams or the binaries produced for the devices we want to run in, the glue code that's required to make maybe the now changed interfaces between the host and the device happen, and also the driver codes for the device themselves. Now, the way that this works is that the devices we generate are custom accelerators. So even though there are drivers provided by the underlying platform vendor, so for example, if you have an FPGA, a Xilinx runtime environment, the hardware we put onto that device also requires a driver that knows about the ABI and the buffers we will be using to stream data. This is also generated by the SDK, by the system integrator part you will be seeing at the end of this webinar. Now, this needs to be linked in here, and so that is one of the device-sided parts. The host-sided parts we already discussed last time. Interestingly, we can also see that this divide between host and device-sided things is reflected in the dialect stack we're using. Certain dialects only appear on the host side, others only on the device side. Something we also haven't seen yet is how these vendor-specific dialects, what we like to call them, make reconfigurable compute easier to access. And one of those we provided for this specifically is base 2. So we've seen tile and how tile allows us to tackle the tensor parts of our HPC kernels. Base 2 is here to tackle the scalar parts of these kernels. That means computation on individual scalars, their data type representation, roundness, and other correctness features. As opposed to tile, base 2 is not application specific. It's specific to a programming model that is common to architectures operating with numerals represented in base 2, hence its name. And it is very well specified for those scenarios to allow you to write reproducible deterministic code that you can run both on the host and the device. Therefore, it forms a small subset that is able to express all these operations and a strong lowering chain in MLIR to implement this. It is therefore one of the dialects that allows us access to the flexibility in the reconfigurable platform, because it allows us to use these parametric types, for example. Now, it also allows you to perform quick DSE. And that is the more interesting part here for our WRF kernels, because typically this kind of transformation would require you to understand the kernel that you try to modify deeply. But here we can do some guesswork, and we can also integrate user assumptions and user constraints much more quickly. We have done this for some of our kernels in WRF that we're using, where we're looking at them from a scalar perspective and seeing how we can scale these parameters for our custom floating point and fixed point types and see how that impacts the error. And in some instances, this provides rather clear results and therefore easy and automatable consequences to how this could be written. In others, this is very application and algorithm specific. However, this helps us to drive the optimization, and this makes it possible for us to perform these data type changes using some manual intervention, but even without having the domain knowledge that would be required to make unit changes or whatever you have in your original code. And the interesting aspect that accelerates the DSE in this base 2 case is that it can be run on the host and a device, because base 2 can bootstrap itself in both environments, and therefore gives us a guarantee about what the result will be and allow us an accuracy simulation. Now, to finalize this segment, I want to summarize again what we've seen so far. Combined in this webinar and the previous webinar were kernel level transformations. In the kernel level, we try to produce HDL that's going to go onto our accelerator. We start from a domain-specific language, and then we go to these, depicted here on the left, higher level dialects that are application-specific. The framework then tries to optimize in these and concretize them to something specific, a specific schedule we want to run on the device. Here we can make use of all the domain-specific transformations given by our dialects, but also those available third-party. A specific implementation of that has to then be written, for example, in terms of loops, jumps, or if we want to go to synthesis, maybe even directly in HDL. Now with MLIR, all of those options are open. We are currently using Bamboo to synthesize LLVM to HDL here. Now, but that is just the kernel-specific part. To make the whole application run, and that's the focus of this webinar, we also have this accelerator level here. And the way that the HPC kernels fit into that accelerator level is that the synthesis process is now driven by a more top-level dialect that is in the same scope as the kernel. So it exists alongside, outside, on a top level. Here, the orchestration of what is supposed to happen and how data is supposed to be flowing is expressed using a data flow dialect, which we can optimize and move around to clearly divide between host and device boundaries. Following this, we have the EVEREST platform tool, which is the EVEREST-specific component of this flow, which is going to take this information and the existing kernel source codes to drive the synthesis process. Given the data flow that we want to achieve, this thing will invoke the correct synthesis tools, collect the estimates, and put them together and formulate them in a way that the Olympus tool can be called. The Olympus tool is less specific to the EVEREST platform and can use this information to derive the system architecture, which it will do by generating HDL. There's also a path from DFG to LLVM here, which is the host-sided path, because as we saw on an earlier slide, on the host side, we also have to provide runtime, and asynchronicity that is inherent to our device offloading is something that the original application probably didn't have, and we're adding here as part of this highly integrated flow. Now, this concludes the new introduction to how HPC kernels are added in these kinds of flows. And I'll now pass over to the data flow kernels, which will also shed more light on what the data flow abstraction I've been mentioning here is.
All right. So now that you've seen how we are integrating deep learning kernels and also general tensor kernels in our EVEREST SDK, I'm now going to show you how we can express data flow pipelines as part of the EVEREST SDK. For that, we are reusing a component called a HUA that we already presented in a previous webinar. And the basic idea was as follows. We express our workflow as a simple imperative program in a pre-existing language such as Rust or Python. And from that, we extract a data flow graph, which we can then transform and later on lower back into Rust or Python code that targets our CPU. For this project, we envisioned that we could extend this support for both languages to also target FPGAs. That would enable us to use application data flow graphs like the one you see here and offload individual kernels to hardware, which could, for instance, contain numerical computations as you've seen them before. A specific use case for this in our project would be the map matching kernel. This is a piece of code that takes GPS data transmitted from cars and tries to map them onto roads in an existing road network. The computation flow for that is as follows. So we get what we call floating car data, which we then project and apply a trellis construction on. And then we use the Viterbi algorithm and interpolation to arrive at clean GPS data where all cars are effectively driving on streets that exist in our map network. And we discovered that about 90% of all computations in this application happen in the projection component. So this would obviously be a very good target to offload because it could yield very good performance improvements. And our idea is here to be able to mark kernels like this one through a specific annotation in our data flow, so on our data flow expression to run on hardware. And this would help us to abstract the fact that specific kernels run on hardware from the developer. And this would also enable us to later switch deployment targets for individual nodes. So let's say we discover later on that, for instance, the Viterbi algorithm could also benefit from being run on an FPGA. So by adding another annotation, we could switch ad hoc to a kernel deployment later on. And so as we tried to use the UHUA component for this, we quickly realized that our previously proposed development is not really feasible. And instead, we decided to use our Rust language still as input, as you can see it on the left-hand side. But instead of targeting FPGAs directly from Rust or Python, we decided that we should go through MLIR, the multi-level intermediate representation that we are already also using in different parts of the SDK. The reasoning behind using MLIR is very straightforward. So on the one hand side, this would enable us to better integrate with already existing tooling in our programming framework, because we're already using that, for instance, for numerical kernels, as you've seen before. But also developing such a generic expression for heterogeneous data flow enables us to also reuse this probably outside of the EVEREST context or within the EVEREST context, but for different applications. So it's not necessarily tied specifically to UHUA. And if we're now running the command that you can see at the bottom, so if we're using our EVEREST Basecamp tool, we can then compile the representation on the left-hand side into MLIR, and a snippet of which you can see here, and I will also show it in more detail in the demo later on. And what stands out here at first is that every single imperative call to a function on the left-hand side is directly mapped into an operator that wraps this piece of code. So we have the function, in this case, it's the find cell function, and this is now wrapped into all the necessary data flow operations that are necessary inside of such a data flow graph, and then execute it as before. We are also using this, so using our newly developed MLIR dialect, we can also explicitly model any input and output to a data flow operator to make it more clear where data flows and why. And as you can also see on the left-hand side in a green color, we are explicitly marking any kernels that are supposed to be run onto on an FPGA. And we're annotating these functions here. And then we generate on the right-hand side also a declaration of this operator, but there is not necessarily a body attached to it any longer. So expanding a bit on this MLIR idea, so how do we support offloading kernels then? So as you've seen, you simply add an annotation, but that is of course not all that there is to it. Functions that are offloaded like this, of course, have to be written in a way that our other framework tools such as Bamboo are able to process it, but this will be expanded on later on. But you can see on the right-hand side that in fact only the instantiation of the data flow graph, which I haven't shown before, which is done using the dfg.instantiate operation, decides where a specific node should run. And in our case here, we are translating this kernel annotation to an attribute called offloaded, which is set to true for all kernels that are supposed to be run on hardware. What we're also doing is taking the hardware kernel and generating all the necessary glue code for it to shield the developer from the complexity of running a piece of code on hardware. So it is very transparent through this annotation that a specific function is not being executed on the CPU, but at the same time, it is made very easy to use it. And of course, also these different, so these annotations allow also to perform dynamic offloading decisions. So if we have a function that is generally eligible to be run on an FPGA, we can make the decision to offload, whether to offload it or not, simply by adding or removing this annotation. And another benefit of using MLIR is also that this representation would also allow us to use kernels that are already written in MLIR and integrate them in our application simply by having such an operator. But instead of just declaring it with nobody, we could add the body written in MLIR, and using this offloaded equals true attribute, we could then also lower that into hardware. Yeah, as I said here, if we remove the annotation, this would mean we are executing it on the CPU. And now I'm going to switch over to a demo and show you a bit more in detail what our MLIR code looks like. So here you can see on the left-hand side the code that I have already shown you on the slides. So this was our input code that we used our OhuaC compiler on to translate into the MLIR representation that you can see on the right-hand side. And in general, our MLIR dialect consists of only very few primitives. So essentially, our dialect models a data flow graph, meaning we need some primitives to express nodes in the data flow graphs and the arcs between the nodes. And we did this as follows. So as you have seen before on the slides, up here we have the different node definitions using the dfg.operator operation, and using this we can define that an operator exists and also what happens inside of it. And as I've also outlined before, we explicitly model any inputs and outputs to this operator. So here we have two inputs. One of them is a vector of map cells, and the other is a GPS position, and we produce from that a simple number. And using this find cell function here, as we have seen it on the left-hand side on line 14. So here we're producing this index from that, and this will then, this then happens here. And what our graph, of course, also needs is to retrieve those inputs, which we're doing using dfg.pull operations, which pulls from the receiving end of, which pulls on the receiving end of our data flow connection, and the result is then transmitted through an outgoing arc to the next node in the data flow graph using the dfg.push operation. So this is all very explicit, which, even though the developer is not necessarily faced with this MLIR representation while using our tooling, can aid in debugging efforts and is also expressive enough to use it in different contexts later on. Then we also have this loop primitive here, which simply ensures that the computation inside it, so the body of this loop, is executed eternally until one of the input nodes that is provided, or output nodes that is provided here as arguments, will be closed. So if one of the inputs should no longer exist, so the pipe has been closed, or if the output node, so the target for our output node is also no longer existing, the computation terminates at this point. And using these defined data flow operators here, we can then build our graph, which all happens inside one function here. So we have our node. So we have our node instantiation down here, where we instantiate all the different nodes that we have defined above for use in the graph. And of course, we also need to explicitly wire the data flow connections, as I've shown you before. And for that, we have typed channels, so typed so that they have a fixed size that is statically known. And we're instantiating those channels here. Each channel has a sending and a receiving side, so an input and an output. And we're then using these channels down here in the instantiation to wire our data flow graph together. So basically the instantiation will spawn one instance of a specific node and wire it together using the provided channel inputs and channel outputs. So we could also take an operator definition from above and instantiate it multiple times by simply instantiating it two times, 3 times, or more often, and wiring them together using different input and output channels. And yes, as I've shown you before, if we go a bit further back here, we have this offloading attribute here, which highlights whether or not a specific operator should be executed on the host side or on the CPU side. All right, and that was it for this very brief demo, just to outline to you how our newly developed data flow graph, dialect, and MLIR is supposed to work. And with that, you can now you will now see how our middle end and back end works, which will be explained by someone else.
Now we will talk about the EVP tool for integration and assembly, seen here in the center of the flowchart. This tool takes the output of any of the front-end flows and organizes it for the back-end. Each of the front-end tool flows will generate key outputs, CPU host code, and potential kernel code. This kernel code includes the MLIR of the Olympus dialect from the kernel declarations and invocations and the actual kernel implementation, which is accepted as Vitis HLS, Bamboo HLS, or HDL code. For HLS kernels, the kernel is synthesized to HDL with the appropriate tool. Bamboo, which can accept MLIR as input, or Vitis HLS. A circuit-based synthesis tool could be slotted in as well. After the high-level synthesis, the resource and timing estimates are inserted into the Olympus MLIR specification. Additionally, platform details are input to EVP. These details include which and how many FPGAs are available in the system and the characteristics of each FPGA, including the resource availabilities and memory characteristics. Also, in the case of multiple FPGAs, a mapping can be specified for which kernels should be allocated to which FPGAs. Here, we see an example of the EVEREST Basecamp command for EVP run after the OHUA flow. The platform has two Alveo U55C FPGAs available, and the output files are specified to go into the EVP out directory. The orange boxes on the left are the inputs to EVP, the relevant platform descriptions, and the MLIR from the OHUA flow. From the MLIR, the kernel implementations and Olympus dialect DFG are extracted to different files for consumption by the HLS and Olympus tools, respectively. Also, the host code MLIR is lowered to an executable, which depends on the Olympus-generated kernel driver library.
We will now talk about the synthesis component of the EVEREST SDK, which in the current version is the open source high-level synthesis tool Bamboo, developed and maintained at Politecnico di Milano. Bamboo is able to automatically generate Verilog or VHDL outputs for a variety of targets, both FPGAs from many different vendors and ASIC libraries. Bamboo is very versatile because it does not only support applications written in C or C++, as is the standard for high-level synthesis tools, but through its Clang frontend, it is also able to synthesize MLIR and LLVM inputs. Bamboo is also continuously updated, and since the last webinar, there have been some improvements. For example, the implementation of fixed point data types and computation has been optimized, and this may be useful for deep learning applications where it is not necessary to keep the whole dynamic range of floating point types, and units working on fixed point types can be faster and consume less area on FPGA. Another major update has been introduced in the integrated verification phase. So after Bamboo generates the Verilog kernel, it is necessary to compare the results of the Verilog kernel with the results of the input application to make sure that this translation was correct. And it used to be that this process had to be done by providing to Bamboo, together with the input program, an XML file with data, with input data that would be fed to the accelerator during the simulation. This had a few disadvantages. So it was mainly it was a very tedious process to generate these XML files from input data that came from different sources, and it was only possible to compare the results of the software execution and of the hardware simulation bit by bit exactly. So in case there had been some approximation introduced during the synthesis process, the simulation would fail, even if the accuracy loss would be perfectly acceptable for the application. With the new co-simulation method that we implemented, it is now possible to write a whole C++ program that acts as a test bench, and this test bench calls the kernel function. In this case, Bamboo will execute the test bench in software until when it arrives at the kernel launch point. There it executes both the software version and the Verilog simulation. And at the end, it can compare the outputs of the two bit by bit, but it can also just allow the user to implement some custom verification methods with maybe it's some post-processing code after the kernel invocation. And this allows, for example, to save data to different files and do some post-processing and comparisons and calculating accuracy drops and so on. And this also allows to use realistic inputs that maybe come from large files, which would be complicated to translate in the old XML format. When writing an application to be synthesized with high-level synthesis and with Bamboo, it is important to add some information about the required interfaces of the accelerator, and this will be needed to integrate the accelerator with other components on the board and with the interfaces. This information can be specified in different ways depending on the type of input file. So they can be pragmas in the C code, they can be encoded into an XML file, in metadata in the MLIR code, and so on. These interface directives specify which protocol to use for each argument of the function of the kernel. And for example, we can use the Bamboo custom interface, handshake protocols, wishbone protocols, AXI, and so on. And in general, the indication is to use AXI for large data structures that will be stored in external memory, and BRAMs for scalars and small arrays so that the access time is limited. For some of the EVEREST use cases that already existed as C++ applications, we chose not to translate them into MLIR because that didn't make sense, considering C++ can be directly synthesized by Bamboo. Because these C++ applications used containers from the standard template library, we just had to ask to the application engineers to not use STL, because STL containers are not synthesizable, they use dynamically allocated memory. But the solution is simply to substitute these STL components with their equivalent from the embedded template library, ETL, which has a maximum size defined in the code. I will now briefly show you what the test bench looks like for the new co-simulation method. This is part of the map matching use case, and you have seen before there are 4 kernels to be accelerated. Here they are: kernel projection, trellis, viterbi, and interpolate. And this is the test bench file. So it contains a main function which starts here, and the main function first prepares the data that will be used for the simulation. And these data are stored in some files, and they will be retrieved from the files and pre-processed. There are some configurations because there are different tests that can be run from the same test bench, and some debug utilities that may be useful to verify the C++ application before synthesis. Then here, the kernels are run multiple times for multiple inputs. When we decide, for example, that we want to verify to simulate the projection kernel here, we just have to specify the dimension of the parameters that are passed by reference and then call the kernel. And when Bamboo arrives at this point of the execution of the test bench, it will run both the software version and the simulation of the hardware kernel. At the end of these 2 executions, we have a lot of post-processing, and in this post-processing, all the output data is written to a file, and the results in this file can be compared with a golden reference. And now I will leave the floor again to Stephanie.
Now we will talk about the system integration tool, Olympus. Olympus generates the FPGA system architecture, including data transfer plumbing and local memory architectures. It is shown here in the flowchart downstream from EVP and Bamboo. The inputs to Olympus include the data flow graph of the kernels, described in Olympus dialect MLIR, and the kernels themselves as either Vitis HLSC code, Bamboo generated HDL, or other custom HDL, as long as it uses standard interfaces. The outputs of Olympus are a kernel driver API library for use in the host code to transfer data and execute the kernels, and the FPGA bitstream. The data flow graph is described using the Olympus MLIR dialect. The key operators of this dialect are kernels and channels. With kernels as nodes and channels as edges, a data flow graph is constructed. Kernels include attributes of the performance and resource estimates of the synthesized kernels. This data informs optimization decisions in the system architecture. Channels include most of the information, as they describe the data movements. Each channel has an encapsulated type, which is the type of the individual elements. Each channel also has a parameter type, which describes the basic organization of that parameter. VRAM type are arrays of primitive data types that require semi-random access. Stream type are data accessed in the same order that it is transferred. And the AXI type is large, irregularly organized, or indirectly accessed data, such as complex ETL structures. Finally, the depth attribute describes the size of the data, either directly as the number of elements in a BRAM array, or the maximum channel depth for a stream array, or the number of total bytes needed for AXI data. We can see here a snippet of a few channels which all connect to one kernel. From the DFG description, Olympus generates an optimized system architecture. The kernels can be replicated to account for data rates or to gain increased parallelism, filling available space on the device. Data flow channels are used when possible to move data efficiently. AXI channels are used by both the Olympus memory management and kernels themselves to get direct access to the off-chip memory. In the case of many available memory channels, such as with high bandwidth memory, bandwidth-targeted optimizations are applied to ensure maximum bandwidth utilization. Private local memories and other memory modules are integrated for data reuse to minimize repeated HBM access. Now, I will show a short demonstration of Olympus. The first thing we're going to do is take a look at the input. So we can peek in this file, and we'll see this is our MLR input. Here are our channels. Here is our kernel. And this should look very similar to that snippet we saw in the slides. Then we can also take a look in here, and we'll see these are our kernel sources. In this case, it's Vitis HLSC code. We can take a look at that. It's just a C kernel doing a mathematical function. And then we can go ahead and run our Everest Basecamp command. We are running the Olympus tool. We have our input file, and we want our output directory. So we'll run that. At this stage, it's only generating the sources for the system architecture. So in this case, it's generating some Vitis HLS sources for a top level for the system architecture. We can take a look at the output, which is organized in this directory structure to be able to generate different variants without clobbering old versions. And if we look in here, we'll see first the CFG, which Vitis needs to be able to connect the system with the memory channels. In this case, we're only using 2 channels, one for the input, one for the output. We can also take a look at our compute unit source. So this is our top level for the system architecture. We have various functions which are data flow pipelined together. We have our read data function. In this case, our kernel was interleaved 4 times, so it's been replicated 4 times because the data is 64 bits wide, and the Alveo U280 has a 256-bit channel width, so we can fit 4 of them onto a channel, so we've replicated it 4 times. And we can see that for each of the different inputs, we have to stream in this data. We have a write data function. It does the opposite. It splits our output from 4 different kernels into 1 channel. And then we have our compute, which just calls upon that kernel body function, which we saw earlier. That was our input file. And then our top level here is taking these inputs and stage chaining all of the streams we need and creating our structure here. Okay, now we can take a look at what else is in the sources. So we have the kernel body CPP and .h again. Those are the same exact kernel sources we saw before. They're just moved, so it's easy to synthesize the whole design together. This kernel.gen.h is a header file with useful pound defines. So next we can look at some host code. So here we have the implementation of all of our API functions for packing the input together, unpacking it on the way out. And this is needed because of that interleaving or any other optimizations we have. The CPU side needs to be able to organize the data the same way that the FPGA expects. We have our kernel function here. So this is setting the arguments and calling upon the kernel. And all of this OpenCL low-level driver code is abstracted away from the actual designer implementing the host code. And then we have our run function here, which is calling upon all these functions in the order they need to be called upon. And down here we have some useful timing code, which we'll see when we execute later, which is surrounded by this if-def, so it can easily be taken out. And then we can also take a look at Olympus generates a sample test bench sort of host code, so you can immediately test if everything's working. It just uses random data as input, but it will show you the pattern of how the API functions need to be called. So at this point, we would synthesize and generate a bit stream, but obviously that takes a few hours, so we're not going to do that right now. Instead, I'm going to run a bit stream I've previously generated, which is our most optimized system architecture for the input code we've just looked at. So if we look here, these are our basic output products. We have an executable, which is our host code, which has all of those driver APIs linked into it. And we have our XDL bin, or the FPGA bit stream. So we can go ahead and run this. Our bit stream requires a couple of parameters. This last one is how many data points we want to execute, in this case. And I'm going to run it with 2 million. So here it's programming the device. We've generated some random test data, like I said, and now we're executing. It should take a couple of seconds. And here we go. So we executed 2 million points, which filled up the entire memory channels 166 times, because it's divided into, this is how much data we could fit in a channel at a time. So it iterated 166 times. And overall, the full execution, including data transfers, took 8.168 seconds. And our total gigaflops, because we know the number of flops each kernel is 43. And it says test passed, so that's great, it worked.
Thank you for checking out our newest webinar on the EVEREST SDK. I hope you found the information useful, and we look forward to seeing you in one of the future webinars.